Okay, quick summary of close to an hour of video on this one idea. Okay. First of all, omega is the rate of change of theta with respect to t. Alpha is the rate of change of omega with respect to t. We have some idea what this means. Omega is the rate of change of the angle of a domino as it falls to the tabletop. Alpha is the rate at which that velocity or that rate of change of position is changing, making this sort of a complex situation. Alpha being the rate of change of omega with respect to t can be calculated as negative 300 cosine theta, where this comes out in units of radians per second squared. We don't want to talk too much about that, but that unit comes in and out throughout the discussion. The alternative would be to put units on the 300, and that would be confusing at this point. Okay, we're going to assume that initially things angled about like this, at theta equals 1.2 radians. Omega is negative 0.1, meaning negative 0.1 radian per second, just moving very slowly about like this, just barely moving at t equals 0. We could have started omega at 0. That would have led to a little bit of discussion in the first increment about why the thing didn't go anywhere. So we didn't do that. We gave it a little bit of velocity. It almost didn't go anywhere, but it did go a little. Okay, so those are our assumptions, and we're going to assume this occurs at t equals 0. And we want to approximate what happens 1 millisecond at a time. So we're going to say delta t is 1 millisecond, or 0.001 second. Okay, before we can do much, before we can figure out what happens in the first millisecond, well, to figure out what's going to happen in the first millisecond, really all we need to do is figure out how much theta changes, how much our angle changes. That'll tell us where we are after a millisecond, and how much omega, our angular velocity, if you wish, our rate of change of angular position, how much omega changes so we know how fast the thing is going after a second. Now we're only going to get an approximation because we're assuming whatever the value of theta is, whatever the value of omega is, doesn't change during that millisecond, but all of a sudden at the end of the millisecond it changes by however much it would have changed if those things would have remained what they are. Don't need to necessarily understand that statement either, but you might want to ponder it if you understand everything else. Okay, before we can calculate the change in theta and the change in omega, we got to know what this rate of change says, and this is a step people tend to skip. Okay, we've got this. You can't, you weren't born understanding this, and you've only seen it within the last week or so. You haven't internalized the meaning of this yet. Hopefully you will within the next couple of days. Okay, so we have these two facts that we have these two rates of change, or these two assumptions that we have these two rates of change. So what do we mean by omega is the rate of change of theta with respect to t? We have to know the definition of rate of change. Rate of change of A with respect to B is change in A divided by change in B. Not many people, even a week later, can tell me that. Okay? Think about why you didn't focus on that, why you don't have that deep in your memory. You should have thought of it, you should have used it, gone back to that definition dozens of times by now. It's the difference between doing mathematics from definitions and solidly based ideas and procedures, and doing it by superstition. Unfortunately, as I've said, the SOL tends to force instructors to do things as much by superstition as by rules and so forth. And that's what you're kind of used to. You have to know the definition. And by knowing the definition, you can tell me that omega, well, the average value of omega, the average value of the rate of change of theta with respect to t is change in theta divided by change in t. So that omega is approximately equal to the change in theta divided by the change in t. And of course that can be written delta theta over delta t. And of course that's identified with the slope of a graph. And people tend to think in terms of the slope of a graph rather than in terms of the definition. Well, it's good to think in terms of the slope of a graph, but you really have to know the definition. Okay. And similar, applying the definition to alpha, which is the rate of change of omega with respect to t. That's change in omega over change in t, delta omega over delta t. Again, it's approximately equal, not exactly equal, because these quantities are changing continuously, and we assume they stay static for a millisecond. So we have a little bit of error in the calculations. Anyhow, let's not belabor that right now. We'll see how that works out. Okay, so now we know that theta is 1.2 radians, omega is negative 0.1 radian per second. We want to find the new values of omega and theta after 1 millisecond, which is equal to 0.001 seconds. Okay. How do we find the new values of omega and theta? Well, we know values of omega and theta. To find the new values, we just have to find the change in omega and the change in theta. Now, we're out of luck if we want to find the change in theta and we haven't made this observation or some other way connected this to the rate of change. But this is the way that you want to do it right now. Develop a little more intuition. You can go back to the definition and you can say what it is. I don't know about you, it would have taken me about a month. So you want to write out the definition very methodically. And you want to keep thinking about what it means so it eventually sinks in. You need to find then the changes in omega and theta, and you use this and you use this. Because why? Because delta t has already been stated. We're going to use 0.001 second for our delta t, and we're going to use that in every step. So delta t is always going to be 0.001 seconds, so we know delta t. Okay? And what else do we need? If we want to find delta theta, we need to know omega, right? Well, right there it is. We've got omega. And knowing delta t, if we want to find delta omega, we need alpha. Well, we aren't given the value of alpha. What we're given, and this is a little bit of a complicating thing, but after a while you get used to this sort of thing. We aren't given the value of alpha, but we're given a way of calculating the value of alpha. So there it is. And we calculate it in terms of theta, and we know theta. So we're going to be able to plug theta in here and evaluate alpha. And then, evaluating alpha, knowing delta t, we can find delta omega. Very straightforward. And we can write out here, well, if omega is about equal to delta theta over delta t, we multiply both sides by delta t. We get delta theta is approximately equal to omega times delta t. Alpha is about equal to delta omega over delta t, so delta omega is going to be approximately equal to alpha times delta t. Applying those definitions, then delta theta is omega delta t. Omega is negative 0.1 or 0.1 radian per second. Multiply that by 0.001 second, we get negative 0.0001 radian. So that our new value of theta is going to be our existing value, 1.2 radians, and I wrote 12, and that led me into a lot of trouble. That would have been better to have been avoided. 1.2, and this is 1.1, and there's one fewer 9 on that. Okay? So now, having written it correctly, our theta is 1.2 radians, and it changes by negative 0.001 radian, and we get 1.1999 radian. Insignificant change, but it's going to start building up. We're only going 1 millisecond at a time. We're going to need 150, 200 steps for this thing to fall, and we're not going to want to calculate them all by hand, which is why we talk about Excel. Okay, so we find so we get our new value of theta. So now we know what our new value of theta is. That'll be in our next step. We'll use that for our value of theta and calculate on. So we want to find delta omega. So we need alpha and we need delta t. We know delta t, same as always. To find alpha, as we've said, we use this. Here's our definition of alpha. We've got to plug theta in here and find alpha. We do that. So alpha is going to be negative 300 cosine of 1.2 radians. And that's going to be pretty close to negative 120. which means negative 120 radians per second squared. You don't have to know that unit, but since I'm kind of, letting units come in and out here, I'm going to kind of give you a preview of that. Okay? So what do? We get alpha is this, delta t is this, delta omega is alpha delta t. We calculate that, we get negative 0.12 radian per second. We add that to this value of omega because that's the change in omega, and this is the value we started with. So we add the change to the initial value, and we get the final value, which is going to be negative 0.22 radians per second. So now theta is almost 1.2 radians, 1.1999 radians. Omega is negative 0.22 radians per second. We can now do the same thing we did before. We're going to find delta omega and delta t. And that, we know what delta t is. We're going to find delta omega and delta theta so that we can find omega and theta after another 1/10 of a second. So there's a little bit of an error there. So what do? Delta theta is easily calculated. It's omega delta t. Omega is now negative 0.22 radians per second. We multiply that by our millisecond. We get the change in theta. And then we're going to, in a minute, add that to our value of theta, but I didn't include that in this calculation. We would add this to our 1.1999 radian, and we'd get our new theta. Then we calculate alpha. We got a new angle. It's almost the same as the old angle. We get almost the same result. Remember, this result's just an approximation I did in my head, okay? If you punch this into a calculator, this is going to be a little different. So anyhow, alpha is going to be this. It's going to be almost exactly the same as it was before because the theta hasn't changed much, and theta is what determines alpha. Our delta omega is alpha delta t. Well, that's an easy calculation. We get this. And our new omega is our existing omega, which is our negative 0.22 radians per second. And to that we add the change in omega, the negative 1.2 radians per second. We get negative 0.34 radians per second. So we see this thing's moving a little bit and speeding up a little bit. We then summarize what we've done on a table. Okay, we have a column for theta, we'll have a column for omega, and so forth. And we just let the table reflect our calculation sequence. We've got theta and omega. We get delta theta by multiplying omega times delta t because of the definition of omega as a rate of change of theta with respect to t. We calculate alpha by plugging theta into the formula for alpha, and we use alpha then to calculate delta omega. We add our delta omega to our omega, and we get our new omega. We add our delta theta to our theta to get our new theta. And then we write down those values here. And in the next line, we do exactly the same sequence of calculations, but based on these two values of theta and omega. So I'm not going to repeat what those calculations were. We just go through methodically and do them. And we write our new value of omega and our new theta here, and we go through the calculation and do them. And Excel will do that very efficiently and very effectively. Now, the one other thing that we probably want to include in our spreadsheet is our time. Remember, our time started out at 0. Well, each step represents a time change of 0.001 second. So our time in the second step is 0.001, and the third step it'll be 0.002, and this will continue, all this will continue. If you're using Excel, once you've calculated this line using cell reference, and let's make sure you, yeah, okay, I can see the edge of the board. Once you've calculated this line using cell reference, you can copy these values down, and now you can drag the rest of this down here, and then you can grab this line and drag it, and you go where you want to go.